when we do our storage, there's a couple things we need to store. We're going to have to store all of the data that will be necessary for crash selection or for crash searching. And then we're going to store all the data that's free. Okay? There's some data that we'd really, really like, but it takes a long time to get. That's data we're going to push till after crash selection. But we'll take everything we can get because we don't know what's going to be useful at this time. Another thing that we're going to store in that database is the code path coverage of our initial test program or our initial test input. And then we're going to store the code graphs for the program that we're fuzzing. So the reason we're going to do that is so that we can easily go back and automate this retesting later and know what tests to go through without going through the input selection. And in this way, you can pretty much automate all that stuff. Another neat thing that you can do is track bug life across different software versions. So if what you're looking for is a bug to sell to somebody who is very concerned with having a bug live a long time, you can automatically search your database for bugs that live in code paths that have been recently patched, but were still not found, because odds are those code paths won't be covered again in an audit very soon. So again, the question is, which crashes do we go and add extra triage information to later on, right? And the answer is, we're only going to go back and triage the crashes that we understand, okay? So if you have a guy that's really amazing at doing low fragmentation, heap, metadata, chunk exploitation, which probably nobody does, but if you did, you'd want to be able to go and find those bugs. So you'd have to be able to search your database and find the bugs that fall into that category, that crash in that specific way, to hand off to that guy. If you pull on a new group of people that have a new specialty or new research comes out and somebody understands it, you want to be able to search for those bugs and hand it off. So the bugs that we find interesting absolutely will change over time. Okay.
So in addition, as part of the triage process, of course, once we get all of these data sources back, the first thing you're going to need to do is some exception analysis. So if your goal is to put the people that are capable of exploiting certain classes of bugs and getting that data into their hands, well, then obviously the first thing you need to do is a little bit of automated exception analysis. And obviously we have some tools like Crash Wrangler or Bang Exploitable. They'll tell you if it's a read AV or write AV. I believe that tooling can do better as we get towards data flow analysis and taint tracking. We'll be able to understand, is this data used further on? If we can apply constraint solving, things along those lines. These are things that we haven't implemented yet, but are part of the process at the end of the day. There are papers out there that discuss these parts of the triage process. And as part of that, there's other things to consider. For example, in Adobe, they use a custom memory allocator. So you may have a guy who's a little fresh off the new vuln dev pile, but if he doesn't quite understand how to exploit the latest Windows 7 heap management, he may be able to understand something like Adobe's heap manager, and you can specialize in that. The data that we're going to need is flows of execution, flows of data propagation within the memory space of the program. To get the code execution, what we're looking for is code coverage. And that comes from a simple block hit trace. The execution order of the blocks infer the actual graph edges. And so you take a simple block hit trace, obviously tie up those edges, and now you have a presentable graph. You can use those runtime graphs to overlay static graphs because, of course, when we're dealing with C++ or other languages that compile in a lot of indirect function calls, you're not going to be able to see the entire attack surface initially or see what code paths could have reached this vulnerable function without overlaying that data. You also are going to want to hook the APIs that have to do with user I/O. So in the case of Windows, you might be hooking open file, read file, map view of section, et cetera. And on the Linux side, the system calls are similar, mmap, read. And we want to mark the data that comes in from those calls as it gets propagated into memory so that we can watch future reads and writes to those address spaces, build a data flow dependency graph, and then follow the actual taint propagation through that graph. And the whole point of doing taint analysis, if it's unfamiliar to you, is to understand what parts of memory were actually touched by these external I/O APIs. So if there's potential data flow coming from a read file, and you've identified that read file is reading from a file descriptor that is supplied by the user, well, obviously, the data that propagates from there is very interesting. That's data that can be modified and manipulated and may be used in this crash. And at the end of the day, we've seen like the automated exploit generation paper came out last year, I think. That we work in the business of writing IDS signatures, and so some of the analysts on our team hopefully can benefit from this type of work because the bytes that were involved in the crash are obviously the bytes that you're going to be looking for in an IDS signature off the wire. And then finally, as part of our process, we need to make this easy to use, like we said. So one way to do that, since we're collecting these giant data sets, I mean, millions upon millions of locations in memory that were modified by user data, hundreds of thousands of blocks or functions that were executed, we need a way to be able to understand this data effectively. And putting it in a spreadsheet just isn't going to do it. So it's common, of course, to use something like IDA and look at graphs. And we've developed some of our own graph visualization. And a couple years ago, I did some research a little deeper on visualization. And there's a lot of scientific studies out there that just say that if the human brain is most acclimated to understanding large amounts of data through vision. So it only makes sense to try to put problems of complex data association into a visual context. So in order to achieve some of these goals, we've started to write a tool set. Not all of the goals that I've mentioned have been implemented, but this is a process. And along with the process, it would be kind of useless if there weren't effective tools to implement part of that process. So I have a tool set called MoFlow. And this is the general architecture diagram. It's a series of libraries. It spans several languages from, I use an external disassembler library written in assembler itself to C# UI, C++ wrappers, and whatnot. This architecture isn't all that important to remember right now, but what is kind of interesting is that we are able to coalesce all of this data into a database or data source, and then make it accessible from several different areas. Like the fuzzer that we use takes advantage of some of the flow coverage as we select which files to fuzz. Also, we have a WinDebug plugin that can take, like if you've ever tried to get a call graph in WinDebug, it doesn't exist. They are able to show you a function disassembly that's broken up by blocks, but they don't actually have an internal representation of the program graph. So by taking some of this data that we extract and putting it into WinDebug, you also have a more effective tooling while you're actually actively debugging the scenario. And here's just a little screen capture. I'm going to show a live demo. Was this the... Are we going to do the demo here after the input selection? Okay. So yeah, we'll get into this in a minute, but here's a general concept of this is the kind of easy-to-use interface you're looking for. You want to be able to navigate the graph, select some input files that you're interested in, collect data about those input files, and intelligently be able to determine how to begin your fuzzing process, and when you find crashes, how to triage that. Like I said, we'll demo that here in a little bit. First, we should talk a little bit more about the requirements and the implementation of what we're working with. So one of the things that was mentioned is attack surface analysis. You know, that's a term that more or less refers to understanding the subset of the code that is actually exposed to external data input. So, you know, in the case of a UI program, a good large percentage of that is all user interaction related through the UI. It's probably not the types of code that we're interested in for looking for network or file-based vulnerabilities. So we need to initially be able to look at the old program, call graph, do some reachability analysis on it, determine which APIs we believe are important, whether they be system calls themselves that take the I/O, or they be wrappers that we define as driver interfaces or you know, wrapper functions and DLLs, for example, and coalesce that down into an interesting area of the program that we're looking for. Next, we need to be able to do an efficient dynamic trace of the potential input files that we're interested in. A lot of people use external tools like that are based on WinDebug, such as PyMay, PyDebug, Process Stalker, whatever it might be. The debugging engine is a great thing, but it's not the most efficient way to trace a program. So we work towards making a more efficient tracer so that when you have a set of 1,000 templates and you're curious which one of these you should start fuzzing to make your fuzzing process efficient, well, every time you increase by about a factor of 10 to 20, that's 10 or 20 more template files you're getting through every couple of seconds. So obviously when we talk about efficiency, the base recording tools and the base analysis needs to be as efficient as possible. And then obviously as part of the input selection, we want to be able to have an interface that shows some form of comparison after you've traced all these files and says, hey, we have this attack surface that we're trying to get to, that we're trying to cover. How many of these files actually hit the areas that we're interested in? Or let's say you know about a vulnerability in a specific structure in a file. And so you add the function that parses that structure to your attack surface, and you say, we actually are interested in not just the overall attack surface, but specifically files in our data set that will hit this area of code. So that's what we're looking for in template ranking. Do we have templates that are even going to exercise the area that we're interested in, and how much are they going to exercise? So in order to get that attack surface analysis, in that architecture graph, one of the things that was listed was a library, libcodis. And it's just a wrapper around a disassembler library that is able to construct call graphs and control flow graphs. And of course, you can use IDA. I've written a IDA script that works on all the versions, so you don't need to have a commercial version, but it exports the important parts of the graphs and the function, the calls and block edges and whatnot. And then, of course, you need to define the APIs. And like I said, there's a set of APIs that will be related to the system functionality, but also sometimes when you open a large program, like let's say Adobe, most of that code is executing in a 20 megabyte DLL, Adobe Reader 32, and there are no calls out to open file, read file, et cetera. Those are all wrappered. So you need to be able to understand at least your input enough to associate the wrapper function with that. And that can be done through dynamic tracing as well. If you do put a hook on read file, and you only actually are interested in where does the execution path get back into this DLL that we're interested in fuzzing, then it can automatically identify this is your exposed APIs. Of course, that's limited through dynamic tracing, and you're not going to get it all at once, but you can merge these graphs. So reachability is a problem. So if you're going to determine which functions on this call graph are actually reachable from an input source or from a taint API, attack surface API, then you need an efficient way to do it. There's a algorithm. It comes from civil engineering, actually, or some other discipline that I came across, and they were doing network graph analysis in a completely different context, where they're interested in relationships of pressure points or something like that in a construction building. Well, we can use that same thing to understand, is this point on the graph influenced by this other point on the graph? That's exactly what they were doing in a physical context, but we're doing it in an abstract context on computer programs. The algorithm is pretty simple. You just keep you have your full list of what's in the graph, and you have a work list of which nodes you're interested in. You throw your APIs that you're beginning with into that graph, and then you iterate. So every time you look at all the edges out of that node that you initially put in there, if there's an edge, then you add the node that it's attached to back into that graph if it's not already been analyzed. So pretty straightforward. People talk about reachability all the time, and sometimes it's like, how do I do that? It's not too difficult. The template code coverage continues on with instrumenting each basic block in the program. And like I said, the debug engine isn't the best way to go. I use Pin, the Pin tool framework. It's similar to Dynamo Rio. It's a just-in-time compilation, more or less, of native executables. It's got its own loading. It caches the functions every time they're referenced. It pulls it out of the cache, allows you to install hook functions and inject callbacks after reads, writes, calls, whatever it is that you're interested in. But you'll see I have some stats coming up, I think, on the efficiency of that. And yeah, and I guess the only other important part of that is file I/O. So when you're tracing, if you've written this efficient tracer or on top of an efficient tracing framework, and you're dumping out to a file every time, well, you've just reduced that efficiency.